So stop and think about this for a minute and pause the video if you need to just think about this. I mean, infinity is not a place that we can, quote, go, right? So how could I possibly prove something about infinity, right? I mean, how can I prove that there's always going to be a larger and larger and larger prime? How do I really know that? Okay? How can I determine that when I'm talking about numbers that are like hundreds of miles long, right? If I type them out in 10-point font. All right, so try to puzzle about that for a minute. How would I prove that the number of primes just goes on and on and on forever, right? When forever is not somewhere I can actually go to, right? It's this kind of out there idea, right? It's a concept. It's not a real place, right? And that's what infinity is. Infinity is a concept, okay? So here's what we do. And actually, before we jump into the proof, here's a little bit of prerequisite math, okay? Because we're going to use this skill later in our proof. If you were doing this problem, you would probably add, right? This would be how your grade school teachers taught you how to do it. Add the 18 and the 12, get 30, divide by 2. The answer would be 15. But if I told you you have to start using division, would you be able to just divide the 2 into one of these numbers? Right? That wouldn't work, right? That would give me 21. Okay, so what happens is when I separate by this plus sign here, in order to divide by 2, I have to divide both parts by 2. Okay, if I do that, then I get 9 plus 6, which is in fact 15, which we agreed was the correct answer. Okay, so I'm going to use this concept later. So anyway, let's take a look at how we can prove this. All right, the logic behind this proof is we are going to say that it's true because it can't be false. Okay, so how do you feel about that? All right, and so again, pause the video anytime you need to and kind of puzzle over this, right? I am going to say it has to be true because it can't be false. Okay? But if I make a factual statement, okay, something that's black and white, there's either infinitely many primes or there's not. There's only 2 possibilities, okay? It's either finite or infinite. There's no in between, okay? So when there's only 2 possibilities, if I can eliminate one of the possibilities, then it would have to be the other. Okay, and so often when I say this to students initially, they feel like this isn't good logic, right? They give this a thumbs down. Okay, but this is actually a very valid way to prove this. All right, and otherwise, how could I prove something about infinity? All right, as I just said, infinity is not a place that we can go to, and so how would I prove that there were infinitely many primes, right, without this technique? So anyways, here's how the proof works. Suppose that it is finite, okay? And if it's finite, then I can list them all. So I start writing a list. P sub 1, that's 2. The first prime, the second prime, the little subscripts telling me what prime I'm on. And eventually I get to the very last prime, right? So this would be like the biggest prime known, okay? I've got them all in a list, all right? So I'm assuming that the primes are finite. All right. And again, this might seem weird to you. I want to prove that it's infinite. There's infinitely many primes, and yet I assume the opposite of what I want to prove. Okay, so how does that feel to you? Again, you might feel like that seems a little bit weird. You're assuming the opposite of what you're trying to prove. Okay, but this is actually a very valid technique of mathematical proof. So anyways, here's what I do. I assume I've listed all the primes. Then I come over here and say, well, then I'm going to make a new number called P. I'm going to take every single prime and I'm going to multiply them, and then I'm going to add 1 to it. And that creates this new number P. Okay, and there's only 2 possibilities for any number greater than 1. A number is either prime or composite. There's no other possibility. Okay, So according to my claim, I wrote a list of all primes, right? Therefore, P wasn't in my list, right? Because P was made by the product of the numbers in the list plus 1. Okay, so P was not in the list. That means P better be composite or I've already contradicted myself. Okay, so P has to be composite. All right, I've just decided that. So then, if it's composite, it has to have a prime divisor. Right, so I'm going to say this is P sub K. I don't know what prime will divide it, but there's got to be some prime that will divide it. So P sub K is going to be the divisor, which means it's going to have some whole number partner. All right, we know that factors occur in partners. So I set up the division problem, right? And here is where, this is why I did that exercise in the beginning. See how it's separated by a plus? And so the only way to do this is to separate. Now, this was the product of all primes, which means P sub K is in there. It's in there somehow. And then P sub R, that's an R, sorry, it's hard to write with my cursor. If I divide this by K, right, K is in there. P sub K is in there, right? So therefore, P sub K will divide it. That's something that we learned earlier in this segment. Okay, P sub K is in the list of factors as part of the product. Therefore, P sub K is a factor. All right, so P sub K divides this. Well, then P sub K would have to divide this, and I'd have to get a whole number. Okay, now if you don't believe me, take out your calculator and do 1 and divide it by any whole number. 1 divided by 2, 1 divided by 3, 1 divided by 4, 1 divided by 5. You can see where this is going, right? If you do that, you're only going to get a decimal. Okay, there's no way to divide 1 by any whole number and get another whole number. It just won't happen. Okay, so what that means then is that P sub K couldn't have been a divisor. That means that my number P, right, this value P cannot have a divisor, right? That means it can't be composite, right? If no prime will divide it, it can't be composite. So now I've got this problem, right? I said P can't be prime. Well, it can't be composite either. Okay, well, for a number to exist, it has to be either prime or composite. There's no other possibilities, right? Well, then therefore, since it's neither prime nor composite, it can't exist. Okay, but then I formed P based on the assumption that there's a finite number of primes. That led me to this P value, which I realized can't exist because it can't be prime, but it also can't be composite. So therefore, by assuming that there was a finite number of primes, I got to a contradiction. So if it can't be true that there's a finite number of primes, right, my assumption that there's a finite number of primes must have been false. There's only one possibility left then, right? And this is called proof by contradiction. It might have seemed weird to you. It might have seemed illogical and not settling well with your intuition when you first heard it. But I have said this is true because it can't be false. All right, because I tried to let it be false and ran into problems every which way I went. Therefore, it's true because it can't be false. And there's the proof. There is an infinite number of primes. Thanks for hanging in all the way to the end on this.